So this video here is going to go over what's sometimes known as the special cases of systems of equations. And that would be when we have no solution or infinite solution. And something that we're going to extend in pre-calc that we didn't do in Algebra 2 Trig is give a rule for what these infinite solutions would look like, so we could then actually produce however many solutions that we want, instead of just saying there are infinite. So just to give a visual of these systems, just like if you have x and y, that creates a line, and systems are the solutions are the intersections of those lines. Well, when we have x, y, and z, it's a three-dimensional graph, and since it's linear, these graphs are just planes, as you can see here. So these are 5 different systems and showing you the different orientations of these planes. So to have exactly one solution, all 3 planes would intersect at exactly 1 point. And it looks like only this bottom graph here, all 3 planes intersect at 1 point where this mouse is. To have infinitely many solutions would mean that all 3 planes intersect infinite times. And that could only happen if the planes intersect like this one, all along a line. Imagine like a book. If you open up a book, if each sheet is a different plane, they all intersect at the spine of the book. So there's infinite solutions along that spine. The no solution would be that there is no point or set of points that falls on all 3 planes, which would be these 3 situations here. Some of the planes might intersect, but not all 3. Okay, so in this example, I'm just going to show you how no solution would happen, basically how you know there's no solution. So the first thing, I'm going to do elimination based on the setup here. So I think I'm going to eliminate z. So here I took equation 1 and equation 2 and added them together because the z and negative z, and that gave me this equation, which I'm going to call equation 4. Then I'm going to take equation 2 and 3 and add them likewise to get rid of z again, and that gives me this. At this point, now it's just treated like a 2-by-2 system. So what I'm going to do is I'm going to multiply this equation 4 by 2, and then subtract equation 5, and I get this. Now, you might do it a different way, but the idea is, in the end, we're going to get a false statement, and that means that there's no solution. So graphically, if we were to graph these 3 planes, there would be no place where they intersect. So again, the idea is, if you ever end up with a false statement, that means there's no solution. Now, on the flip side, this is a situation that's going to end up being infinite. So let's see how this works. Since we have this y equals, I'm going to substitute instead of doing elimination. So I'm going to take this y here, and I'm going to substitute that into equation 1. And I'm going to substitute it into equation 2. By doing that, that gives me this equation 4 and equation 5. Okay, so at this point, now I'm going to take 4 and 5. I think I'm actually going to scale them down. I'm going to take equation 4 and divide all this by 3. And then equation 5, I'm going to divide it all by 5. That's going to allow for this negative 5z and 5z. So now when I add these equations together, I get 0 equals 0, 0 equals 0, and that's true. And when that's the case, when all the variables cancel and we get a true statement, that's an indication that we're going to have infinite solutions. Okay, now we don't want to stop there. We want a rule, or basically a way to figure out what these solutions are. So the idea is this: you're going to choose one of the variables to be what I'm going to call the base variable. So in this case, since here our final system is in terms of x and z, I'm going to choose one of those to be the base variable. And just for this example, I'm going to choose z. Okay, so z is just going to be z, what I call the base variable. Okay, so now what we'll do is we're going to find x and y in terms of z. because then if I want a specific solution, I just pick any number I want for z, and I can plug it in and find the corresponding x and y. So just to see how that would work, starting back one step, like with this equation, I'm solving for z. And when I solve for z, I get this. Or sorry, solve for x, sorry. I want z to be z, so I need to know what x is. So I'm going to solve for x, and notice how it's only in terms of z. So this is what's going to go in the x location right here. Okay, and now I need y. Well, to go into y, I'm going to have to plug the x into equation 1, 2, or 3, and then solve for that y. And now equation 3 is pretty nice because it's already in terms of y. So I plugged x into the x, and I now get y in terms of z. So in the end, again, notice how my base z is just z, and x is this, and y is this. So now what's nice about this is, let's say I want a specific solution. Just like if I say, hey, give me a solution, any solution. I can pick any number I want for z, and it's going to work. There will be some solution with that number for z. So I'm going to choose 4, and you'll see why 4 in a minute. So then z is 4. Y is going to be that number 4 plus 5. So this is going to be 9. Again, I'm writing with my mouse, so it's a little bit scratchy. And then x, likewise, z was 4, so I'm going to plug 4 in there. I chose 4 because I have this divide by 4, so the math will work out nicely. So negative 5/4 of 4 is negative 5. And then negative 5 minus 5/4. This is 1 1/4, so that would be like negative 6 1/4. That would be the x. So that's how we can use this general rule to come up with any points we want. So again, I could choose a different z value and come up with another point that's part of this infinite system.